Today's topic is bioreactor. A bioreactor refers to any manufactured device or a system that supports a biologically active environment. It is a vessel in which a chemical process is carried out, which involves organisms or biochemically active substances derived from such organisms. This process can either be aerobic or anaerobic. Bioreactors are commonly cylindrical and ranging in size from liters to cubic meters and are often made of stainless steel. Organisms growing in bioreactors may be submerged in liquid medium or may be attached to the surface of a solid medium. They are sterile vessels with temperature controllers and gassing facilities required for starting a biochemical reaction. Control over temperature, moisture, pH level, oxygen level, and stirring rate will yield the most suitable condition necessary for maximized cell growth and productivity. Design of a bioreactor. First one, construction of material. The material should have the ability to withstand high temperature and pressure. It should provide a smooth surface. It must withstand repeated sterilization with high pressure steam. It must be corrosion resistant to prevent trace metal contamination and non-toxic to culture. Small-scale bioreactors are made of glass and large-scale bioreactors are made up of steel. Second one is aseptic sealing. It is used in order to prevent contamination. There are three types of sealing: glass-glass sealing, glass-metal sealing, and metal-metal sealing. Third one is aeration and agitation. This is affected by impellers or agitators, baffles, and sparger. Impellers or agitators. It consists of shaft with 4 to 6 blades and motor to drive. It helps in homogeneous mixing of nutrients and air. Baffles. It is vertical, radically located 3 to 4 blades. It is necessary to enhance aeration efficiency and prevent vortexing. Sparger. It is a loop pipe with small holes in the lower part of the bioreactor. It is used to provide filtered air to the bioreactor through bottom in the form of air bubbles. Fourth one, mechanical foam breaker. For elimination of foam, an upper tray with a special rotating funnel-shaped disc-type mixer is installed in the bioreactor's upper cover. Fifth one, Auto-titration Unit. It is filled with acid or alkali and helps in the regulation of pH. Automated titration conducted in buffered environment of zero point 0.1 molar phosphate buffer adjusted to pH 7 using NaOH and HCl. Sixth, compressor. It is used to pump air under pressure to promote aeration and mixing. Seventh one, filter. It is used to filter the air supplied by the compressor before it enters the bioreactor. Three types of filters. First one, membrane filters. These are made up of cellulose acetate and nitrate with a constant pore size of 0.2 mm, and it is quite easy to maintain. Packed bed filters. It contains glass or cotton wool packed through which air is passed. It is susceptible to compaction and wetting, thus causing channeling. Cartridge filters. It contains stainless steel or polycarbonate cartridge. They are more reliable and durable but are very expensive. Eighth one, sensors. There are 7 sensors or control elements that should be considered routine for most of the bioreactors. They are temperature, airflow, pressure, agitation rate, pH, dissolved oxygen, and foam. Stages in a bioprocess. There are three main stages: upstream processing, bioreaction, and downstream processing. First stage, upstream processing. The raw material is either from a biological or non-biological origin. Firstly, it is changed to a more suitable form for processing. This is completed in the upstream processing. The stage involves chemical hydrolysis, preparation of liquid medium, parting of particulate, air purification, other preparatory operations. Second stage, bioreaction. After upstream processing, the resulting material is moved to one or more bioreaction stages. The bioreactors form the base of the bioreaction stage. The bioreaction stage consists of three operations: production of biomass, metabolized biosynthesis, and biotransformation. Third stage, downstream processing. The material which was created in the bioreactor needs to be further processed to change it to a more useful form. This process consists of physical parting operations which comprise of solid-liquid separation, adsorption, liquid-liquid extraction, distillation, and drying. Next is classification of bioreactors. On the basis of mode of operation: batch, fed batch, or continuous. Batch bioreactor. It involves filling the bioreactor with the medium and inoculum and working the reactor without adding nutrients or medium until after the growth profile is complete. Continuous bioreactor. It involves the reactor being continually fed nutrients and medium into the vessel as the reactor is continually harvesting the material. As there is material constantly being collected, continuous process can result in bigger volumes of harvested material and longer bioreactor campaigns. The downside to longer bioreactor campaigns is that it significantly increases the possibility of contamination. Fed batch bioreactor. Fed batch bioreactor processes are the most common reactor process used. The process begins with a lower starting volume and feeds nutrients and mediums on a planned schedule without removing the harvest material. After the process is completed, the material is harvested for downstream processing. Second, based on the presence or absence of oxygen and requirement of stirring. First one, non-stirred, non-aerated bioreactors. These are used for the production of traditional products such as wine, beer, cheese, etc. Second one is non-stirred aerated reactors. These are used much rarely. Third one, stirred and aerated reactors. These are most often used for the production of metabolites which require growth of microbes which require oxygen. Most of the newer methods are based on this type of bioreactors. Third classification based on the method of growing of microbes. First one suspended and second one is immobilized. Fourth one based on the process of requirement, that is aerobic, anaerobic, solid state and immobilized. Fifth one on the basis of the microbial agent used, that is based on living cells and which employ enzymes. This is a diagrammatic representation of a typical bioreactor, and you can see this is a cylindrical vessel with a domed top and a bottom, and the reaction vessel is surrounded by a jacket which is provided with a sparger at the bottom through which air can be introduced, and the agitator shaft is connected to a motor at the bottom. The reaction vessel has side port for pH, temperature and dissolved oxygen sensors, and above the liquid level the reaction vessel connections for acid, alkali, antifoam, chemicals and inoculums are located.